There we go. Okay, so as we were saying, right, we're talking about rates, and the example that we went with for rates was miles per hour, right? But we were also saying that a rate is basically a velocity, right? But you could also have a rate of a rate, right, at which the rate is changing, and that's the acceleration. And then I was just bringing this up right here. If you have, let's say, miles per hour, and you multiply it by a time, what does that entail? So what do you end up with? So let's get some numerical values into this. Let's say something was traveling at, I don't know, 7 miles per hour, and this something that's been traveling for 7 miles per hour has been traveling at that rate for 2 hours. Does anyone have an idea what would this represent algebraically? What have I written down here? When I have a rate of something traveling, right, which is, let's say, 7 miles per hour, and they've been traveling for 2 hours. What's the result of this mathematical operation that I've written out here? What do you think would come from this? If I told you, hey, this thing is traveling at 7 miles per hour for 2 hours. And Brian, that is correct. That's the total distance traveled, right? Rate times time is just equal to distance. It's just equal to distance. This is nothing new, right? Or maybe it is new. I don't know if you guys have seen this before, but this is a standard equation that hopefully you've learned back in algebra or IM1 or a long time ago, right? So this right here, 7 miles per hour for 2 hours, this person or this thing or whatever this object is should have traveled a total of 14 miles, right? 14 miles, right? That's what this represents right here algebraically, right? Does that make sense, guys? Like if you're in your car and you're going 60 miles per hour and you've been driving for 2 hours, doesn't it stand to say that you've traveled a total distance of 120 miles, right? Hopefully. Right? Now, I don't know if you've gone like 60 miles one way and then 60 miles back the other way. That means you traveled a total distance of maybe 0. Or I'm sorry, your total distance is still 120 miles traveled, right? But you ended up at the same location. So you haven't changed your position, but you did travel a total amount of time. Total amount of distance. Yeah, sorry guys, getting distracted. Anyways, getting sidetracked. But yeah, the displacement would be 0. That's right, Monica. I'm getting ahead of myself. Total distance, displacement, velocity, all these things. Fun stuff to look at, but where am I getting with this for this calculus class? Well, let's say here, let's say this thing right here, we call this velocity, right? Velocity. And let's say velocity is traveling at a constant rate of 7 miles per hour. I don't know why I went with 7. I just picked this random speed. 7 miles per hour, is that like the speed of someone running? Do you think is that like a possible speed for someone running, someone jogging, someone walking? How fast is 7 miles per hour? Is that slow or is that fast for someone who's traveling on foot? I'll let you guys tell me. Anyways, here's the idea. If I were to graph the function of this velocity right here, let's say I have an XY axis right here, right? There's no negative values here, right? Let's just say in the x-axis here, it's going to be in a function of time, right? And the y-axis here is the velocity, right? Which is a function of time, okay? So let's say this person decides to go for a run. They start running at 8 a.m. because they're healthy, you know? And they decide to run for 2 hours, right? They decide to run for 2 hours, which is going to end at about 10 a.m. Okay? And when they start running, right, they start running at this speed right here, which is the speed of 7 miles per hour, right? And they run at a constant speed the whole time. They don't speed up, they don't slow down, they're like a machine. And they run all the way over to here at 7 miles per hour the whole time until it's 10 o'clock. And my question is basically asking, what is the total distance that this runner traveled, right? And that's exactly what we were able to find out if you multiply these two numbers together. But do you know why we just multiply those two numbers together? Any ideas? How did someone come up with this idea of distance is equal to the rate times the time? You ever thought about that? How do we know that distance is equal to rate times time? I know I never thought about it. I was given that equation when I first learned it in Algebra 1. And then the teacher went ahead and gave us an acronym to help remember distance is equal to rate times time. And they told us just to remember dirt. And I laugh about it now because it's like, I never actually understood why that is the case, but I did know how to find and calculate distance given a rate and a time. But never really thought about why rate times time is equal to a distance. But here's the time to start. Take a look at this. Take a look at this. If I graph a function of velocity, right? If I graph the function velocity as a function of time, right? How fast something is going, which is up here on the y-axis, it's going at 7 miles per hour, and how long it travels for, which is from 8 a.m. to 10 a.m., right? From 8 a.m. to 10 a.m. What do you notice that it makes here? It makes a nice little rectangle, doesn't it? It makes a nice little rectangle. With the height of this rectangle, right, is 7, right? That's what this height is from here to here. And then the base has a base of what, guys? Someone help me out here. What's the base? It's the base of, well, what do you think? What do you think? 2. That's right. It's a base of 2. And when you look at that, right, we can actually see a rectangle there. And we can calculate the area of this said rectangle, can't we? And the area of this rectangle just comes out to be 14. Now, with the units that are in place there, it's technically 14 miles, right? But it kind of makes sense, right? When we calculate this area for this little spot right here, it calculates the total amount of whatever it was that your velocity or your rate was measuring without the time, right? So this works for almost anything that has a rate, right? At a rate at which something is going at. So let me give you another example of this. But this one's just if I was doing distance. This one's an easy one to see, right? Because hopefully it makes sense. Like when you travel somewhere, how long you're traveling, at how fast you're traveling. It kind of makes sense that that's the total distance you travel. Now that doesn't necessarily it's not necessarily the only thing you can do with your rates. You can also calculate total accumulations or sums of different things. So let me show you one. Let me show you one right here. I'm gonna have you guys. I'm gonna cheat a little bit here, and I'm gonna copy and paste this next problem. So I'm gonna give you a little bit of time to copy this down. So let me go ahead and put this over here. So let's take a look at this example right here. We had that example up there. This example, let's say, consider a snowstorm that starts at 3 a.m. Over the first 2 hours, the rate of snowfall increases from 0 to 1.2. So it's no longer a constant rate. The rate is increasing from 0 snowfall all the way up to 1.2 inches per hour, right? So the rate here is no longer miles per hour, it's inches per hour. And it's not someone running, because that'd be ridiculous. Who's running at 1.2 inches per hour? Maybe a snail, I guess. Can you imagine taking an hour to go 1.2 inches? Me. Is it you at like 6 a.m.? Time to wake up and get to the bathroom. All right, that's 1 inch. I need another hour to move another 0.2, right? Is that how that works, David? I think I'm like that in the morning. But anyways, so we're not measuring distance in this case, right? We're measuring the rate at which snowfall is increasing, right? The rate at which snow is falling. That's not what I meant to say. The rate at which snow is falling. And it's in the first 2 hours, it has no snowfall and it increases to 1.2 inches per hour. For the next 3 hours, it continues to fall at 1.2 inches per hour. So once it gets to that 1.2 inches per hour rate, it stays there. It stays there. It stays constant there. It just travels across there constantly from, it seems like, the next 3 hours. So it's 2 hours after 3 a.m. So I think it's like 5 a.m. And then it travels like that all the way up to 8 a.m. And then after 8 a.m., it begins to taper off, meaning the rate starts to decrease at a steady rate until the snowfall ends at 10:30. Find the total amount of snow that falls during this storm. All right, let me zoom out a little bit there. And let's go ahead and have this. Let's draw myself an XY axis here, and let's talk about this. I'm gonna make it a little bit wider, right? And let's make that black there. I'm gonna make it a little bit longer because it's gonna be the time that we're dealing with is it's starting at 3 a.m. and it's going all the way to 10:30 a.m. So that's a pretty long time scale, right? So on the x-axis here, we're gonna have the time, right? That's gonna be our independent variable there. And this thing starts off at 3 a.m. So I'm going to make those tick marks here. So there's 3 a.m., 4 a.m., 5 a.m., 6 a.m., 7 a.m., 8 a.m., 9 a.m., 10 a.m., 11 a.m. So let's write that out. 3 a.m., right? 4, 5, 6, 7, 8, 9, 10, and 11. And of course, it stops at 10:30, so it's going to be between 10 and 11. All right, so let's take a look here. At 3 a.m., they tell us that the snowfall is currently at 0 inches per hour. So that's going to be right here, right? Now, what is this over here? This is not the velocity this time, right? This is the rate, right, of snowfall. The rate of snowfall, right? Meaning, once you find the area that we're going to be dealing with, we're going to be finding the total amount of snowfall. Keep that in mind. Oh, I shouldn't have said that. I think I just gave away the problem. It's okay. We'll do more examples. So check this out. How should this graph look? How should this graph look? It says here, over the first 2 hours, so if it's 3 a.m., what time do I stop at for the after 2 hours? I don't stop at 4, I stop at 5, right? So the first 2 hours is from 3 to 5, right? At 3 a.m., there's no snowfall, and then 2 hours later, snowfall has increased up to 1.2. So at 5 a.m., the snowfall rate is now up here at 1.2 inches per hour, right? And that's right here. That's this guy right there. So the snowfall has been increasing, right, from 0 to 1.2. So it's been doing something like this. It's been going up to that point. Bam, like that. You guys okay? Now, for the next 3 hours, it continues to fall at that rate for the next 3 hours. So the next 3 hours would be from here at 5 a.m., 6, 7, 8. That's the next 3 hours. And for the next 3 hours, this thing falls at a constant rate of 1.2, meaning it doesn't increase, it doesn't decrease, it just falls at a steady rate of 1.2 all the way till 8 a.m. That right there. Okay? And then after 8 a.m., it begins to taper off, decreasing at a steady rate until the snowfall ends at 10:30. So it goes down like so, all the way down to 10:30, like so. So if you look at this, right, earlier, right, I'm gonna go back and forth a little bit here, so I'm sorry if you're still copying this, but if you go back up here, right, if I had a rate, right, we called it the velocity, but it's basically the rate of position change, if you think about it that way, rate of position, right, changing, or let's just go with rate of position, right, miles per hour, right? When we calculated this area underneath this line right here, it gave us the total, I guess we should call it rate of distance maybe. Yeah, let's go with that, right? It gave us the total distance that it traveled when we calculated that area. And I look at this problem right here, I have the rate at which the rate of the snowfall, right, of how much snow has been falling. Now, if I can somehow calculate the area underneath this line, I could calculate the total amount of snow that has fallen from 3 a.m. all the way to 10:30 a.m., right? That's the total during this storm. The only problem is, how do I calculate the area of this shape, guys? What does this thing look like? How would I calculate this area if I was told that I have a rate at which something is changing by, and then I also have a time from when it starts to when it ends? If I only knew what this shape was called. Wait on you guys. Anyone know what this shape is? Do you guys recognize the shape there? Ooh, you could separate it into a square and 2 triangles. I like that strategy. And then Brian also says that we can call this thing a trapezoid. So which way is the correct way, guys? Should I cut this into 2 triangles and a rectangle? Or should I just take the area as a trapezoid? And yes, Monica, a trapezoid is a quadrilateral. You're right. It is a 4-sided shape. So which way is the correct way? Should I calculate the area, right, of the 2 triangles, add them together, and add the area of the rectangle? Or should I find the area of the trapezoid? Which one was the correct way? Cut it into 3 tetralateral those, I don't think those are real. What are those words, David? 3 tetralateral triangles. I don't. Equilateral. Oh, man. I mean, you could, but I don't know if you can actually easily cut them into equilateral triangles. That'll be a little bit more difficult. But here's the deal. As you can see, I'm a great speller. It's a typo, David. But I'm going to tell you right now, either method is fine. If you know the area of a trapezoid, right? How to calculate the area of a trapezoid, which is 1/2. I believe it's 1/2 base 1 plus base 2. Right, I read an I there. Base 1 plus base 2 times h. Right? If you know that formula, you can go with that formula. And if you don't know formulas for these random shapes, then go with the formulas that you do know. And if you want to go with the triangle, rectangle method, then let's go with that one. I'm going to go ahead and calculate it that. Okay? So check this out. If I'm trying to calculate the area underneath here, I'm just going to calculate the area of each of these shapes here. So I'm going to first of all calculate the area of this triangle right here. All right, so to calculate this area, this has a base of 2, right? Can you guys see that? It has a base of 2, and it has a height of 1.2. It has a height of 1.2. 1.2 right there, and it has a base of 2 from here to here. You see it? So there's a little triangle there. Calculate the area of that triangle. That's just going to be 1/2 times the base, which is 2, times the height, which is 1.2. So 1/2 base times height, well, the 1/2 and the 2 cancel out. The area that I have in here is going to give me an area of 1.2. That's the area of that triangle right there. Okay? Now, keep going. This thing right here has a base from 5 all the way to 8. That's a base of 3. Yeah? And it has a height of 1.2. So this area right here is going to give me a base of 3 times the height of 1.2. So when you multiply that together, that's going to give you an area of 3.6. 3.6 inches of snow fell between the times of 5 and 8 a.m. 1.2 inches of snow fell between the times of 3 a.m. to 5 a.m. We're almost done. This height right here is still 1.2. But this right here, the time from 8 to 10:30, who's got the time for that? What is that time from 8 to 10:30? 2.5. That's right. So to calculate the area of this last triangle, it's going to be 1/2 times the base, which is 2.5 instead of 2 this time, and times that by 1.2. Thank you, Monica, and thank you, Jocelyn, for typing out and making sure that I'm not just talking to myself. I always appreciate it when you guys type in the chat. Sam, David, all of you guys, Eric, I do appreciate you typing out and making sure that I realize that I'm not just talking to myself. All right, so multiply that together here. Let's see here. 1/2 of 2.5 times 1.2. Man, fractions with decimals. I'm just going to go ahead and use my calculator for this. Unless you guys got it. Were you guys able to calculate what 1/2 of 2.5 and 1.2 is? I mean, kudos to you. I think you guys might be able to do it, but I'm going to be lazy. 2.5, and then, of course, multiply that with 1.2. Boop, boop, boop. Comes out to a nice 1.5. That's not bad. 1.5. So here's my question. Find the total. Now here's what my directions are saying. Find the total amount of snowfall during the snowstorm. Well, it's basically just how much snow fell between 3 and 5, how much snow fell between 5 and 8, and how much snow fell between 8 and 10. And if you just add those all up together, that's going to actually give you, let's see here, 1.2, 4.8, 5, 6.3. So if you add them all up, how much snowfall has fallen during the storm? I would say it's 6.3 inches of snow. Yeah, that's it, Monica. We add them all up, right? And that's it. And that's the neat thing you can do with if you have a rate. If you have a rate of something, right? And it doesn't even have to be a constant rate, right? You can calculate the total of whatever that rate is of. Grammatically, that sounds wrong, but you understand what I'm trying to say. If I have a rate of distance that someone's traveling, you calculate that area, you calculate the total distance they travel. You have a rate of which snowfall is falling at, you calculate the area, you calculate the total snowfall you've had over a specific set of time, right? So you can actually do this for a lot of things as long as you have a rate of things, right? So it's a little weird, I know, but it's It's not too bad, right? It's not too bad. And this doesn't have to, like I said, when you deal with rate problems, when you first learn them in algebra, they always do it with like miles per hour or feet per second. It's always a distance that you're trying to calculate. How far away is this boat as it travels down this river that's going upstream at this rate, but the boat's going downstream at this rate? After 5 hours, how far has the boat traveled? It's always the same type of problems like that. It's always a boat traveling down a river, or it's always a person running or a car driving away and another car that needs to catch up at the same speed. I need you to understand that when you're dealing with rates, it's not always a distance. Sometimes it could be a summation of different things. And my favorite example is, what was it, 2 years ago, or was it last year? 2 years ago. I'm telling you, on the AP exam, they love rate problems on there. And I kept saying, I think I said this in this class before, the problem on the test was a rate at which sand was washing up on a beach and how much sand was being washed off a beach. And it sounds complicated, but if you think about it to its bare bones, with that rate at which how much sand is washing up, over time you could calculate how much sand has washed up on that beach. And same thing with it being washed off the beach. I went to a conference and a training. The other rate problems that showed up was instead of like how much sand was being added to a beach, this one was hilarious to me. It was the rate at which people were getting onto an escalator. They had a function that calculated the rate at which people got onto an escalator. So if you calculated that rate, and over a set number of time, you could calculate how many people got onto an escalator. And I don't know, I thought that was kind of neat. It doesn't necessarily need to stick with just exactly what you're thinking of, which is, or what I was taught, which was always, oh, it's always feet per second. Oh, it's always miles per hour. But it actually could be as fun as how many people per minute getting on this escalator. I know, I'm rambling again. Let me stop rambling. Okay. I want you to try one. Okay, I want you to try one. Okay, let's say let's say here, a printer warms up after warms up after 1 minute. Okay. It prints at a rate of 5 pages per minute. Let's go with at a steady rate of 5 pages per minute once it is warmed up. Okay. How many pages can be printed after 3 minutes? So my wording is terrible on this, but I'm hoping you guys understand here. When you start up the printer, right, at t equals 0, the printer is printing 0 pages. But it works its way up after 1 minute to 5 pages per minute. So I'm not going to have you guys do this on a Pear Deck for me right now, unless you're watching a video recording of this. But for right now, can you guys tell me, what do you think this graph would look like if I was to graph the rate at which a printer is printing out these pages? So here's my drawing right here. Let's make that black, right? And it's going by pages per minute. And down here, it's going to be the time, but this time the time is not in hours, the time is in minutes. The time is in minutes here. Monica's saying it's a rectangle. Now, it's a rectangle. Brandon's going, it's a rectangle after a minute. After a minute. Because it does what? It needs to warm up, right? So after a minute, it does get to this line right here of 5 pages per minute. Right, 5 pages per minute. So after 1 minute, it's going to be right here. And a rectangle until when? It is a rectangle, and it's going to start after 1. That's good, but until when? Well, forever, isn't it? It's going to be a flat line all the way across. But what do I care until? What do I care until? Until 3 minutes. Until 3 minutes. That's right. So that's true. From 1 minute to 3 minutes, I can actually calculate, right, how many pages were printed. But what about from 0 to 1? What about while it's warming up? Well, it's going to be warming up at a steady rate. Well, it prints as a steady rate after that, but let's just assume for our sake right now that it warms up at a constant rate, right? So from 0 minutes to 1 minute, let's just assume, and it's bad to say that, but let's just assume that it warms up at a constant rate from 0 all the way up to 5 pages per minute. So the rate at which the rate is changing, right? As David was saying earlier, what's a rate of a rate? Well, that's how much the rate is changing. The rate of this rate is changing from 0 minutes to 1 minute, and it goes up to 5 there. So can you guys do that real quick? Calculate this problem real quick. What do you get when you calculate this one? How many, can you calculate what I'm asking for right here? How many pages are printed after 3 minutes? Can you guys do that real fast? Take a minute. Don't type it out to the chat right away. Just take a second, calculate it. I'll give you guys a minute here. How would you calculate the total number of pages that are printed after 3 minutes here? I just realized I'm asking like a bunch of questions. Just take your time, take a second. Calculate the total number of pages that can be printed in 3 minutes. In 3 minutes. You know, I apologize in advance that I'm rambling, but this is one of the things that I love about calculus is this. Everyone always likes doing like derivatives, right? And just well, not everyone, but a lot of people do when they get into calculus. When I first got into calculus, I loved knowing like, oh, that's the product rule, that's the quotient rule. But what's neat about this is just once you truly understand it, you can start looking at these random situations. And you can start applying some calculus to it. Anyways, we haven't applied any calculus yet, right? We're just in theory right now. But here we go. If I was calculating the total number of pages, I technically just need to calculate the area, right, of each of these shapes here. I can calculate the area of this guy right here, right? And I can calculate the area of this guy right here. If I add those two together, that should tell me the total number of pages that gets printed out. So let's take a look here real quick. So the area from here to here, right, this has a base of 2, has a height of 5. So the area here would be 10. Area here would be 10. And speaking in terms of this word problem, that 10 means that there are 10 pages that gets printed from 1 minute to 3 minutes, right? That's 10 pages that gets printed there. Now that's not the total number of pages that gets printed in 3 minutes, is it? What's the total number of pages that gets printed? Well, how many pages get printed here? Well, from here to here, we have a base of 1, right? So if I calculate it using the area of a triangle, because that's what this looks like, a right triangle here, I'm going to have here 1/2 times the base times the height. So how many pages gets printed there? 1/2 of 1 is just 1/2. What's 1/2 of 5, guys? 1/2 of 5 is what? 2.5. So while this printer is warming up for that first minute, it prints 2.5 pages. It prints 2.5 pages. And then after, from 1 minute to 3 minutes, it prints 10 pages in total. So how many pages does it print in total after 3 minutes? It prints a total of 12.5 pages. That's what happens. So once we look at it at 3 minutes, there's still half a page being printed. But that's the idea here. So when you have these rate problems, you can actually calculate totals of things just by multiplying the base times the height and calculating the area that's underneath that curve, underneath that line, right? I'm gonna call it a curve, but yeah. Now, this is not calculus based, right? This is stuff that we just do and we take for granted. Like I said, when you first learn distance is equal to rate times time, they rarely show you a graph of the rate at which something's traveling for how long it's traveling at and make that connection that you're just calculating the area, right? But that's the idea when you do this, when you first learn this. Now, the reason why they don't really show you a graph of it is because you don't really need to know the graph of it when you're calculating those problems, because the car is always traveling at a constant speed, right? Or it's increasing at a constant speed. It's always increasing by like a line rate or flattens out, right? But you know that when you guys sit in a car, or at least I think you guys have driven before, at least sat in a car, no car ever goes at a constant speed like this and then flatlines and then slows down at a constant speed, right? Especially if your parents are a crazy driver or you're a crazy driver. When you accelerate, you don't accelerate a nice like woo, right? Some of you guys probably step on the gas and go whoa, and then slow down when you see a cop, right? Or maybe your parents do. I don't know how you guys drive it, but it's usually like a curve, right? You speed up to a specific speed, and then you kind of like go there at that speed. If you're on the freeway, hopefully you're going like 65 miles per hour, and you speed up kind of fast to get onto the freeway, and then you kind of like flat line out like that, right? So my question is this here. What happens if I was looking at something like this, right? And let's say I was graphing out this function right here, but let's say instead it looks like this here. Here we go. Make that black. Now, what happens if the velocity this time, the rate at which is the rate that you're dealing with, let's say the rate this time over here is, let's say it's the velocity, and it looks something like this, right? And it looks something like this. And you've traveled from time A, which is right here, all the way to time B. Let's say that those were numbers. Just picture them to be any number that you want. From here to here, how would you calculate this right here? The idea is still the area, right? The area underneath from here to here. Now you can calculate the base area, or I'm not sorry, the base of this shape, right? It's just how far that is. That's just a straight thing. But you'll notice here that the height is going to vary depending on what time you're at, right? At base A, the velocity is this particular speed, but right next to A, at this right here, the velocity is changed, and it doesn't change at a nice line, right? It changes at a curve, and then right next to that, it changes as well. So it changes all the way across here. And this is where calculus comes into play now. We need to be able to calculate this area, right? But it doesn't make a simple geometric shape for us, right? It makes this weird little curve, and we got to find a way to calculate that area pretty much. So what we're going to do today is learn, first of all, how to estimate that area, right? We're going to learn how to estimate that area. And we're going to estimate that area using, well, rectangles, pretty much. And you'll say, not me, we used a rectangle over here. How's that any different? We're going to be using rectangles to estimate this thing. So I'm going to draw a rectangle here to estimate that area for this spot right here. And you'll notice that this rectangle will overestimate this area by a little bit, and it'll overestimate the area by a little bit there. But of course, over here, it'll underestimate the area by a little bit right there. You see that? So we're going to use the rectangles to help us to measure this out. And we call this the rectangular approximation method. The rectangular approximation method, if you want to write that down. But the idea is you can have any type of curve, and it's let's say it's a graph of velocity, right? Graph of velocity, and if you calculate that area, you can find out the total distance of something traveling, right? But again, like what happens if it's not a nice flat line like these guys? Well, then we got to use our calculus abilities here. But before we get to the calculus abilities, we're going to use the first step, which is rectangular approximation. Okay, rectangular approximation. So let's go ahead with this next example right here. Finding distance traveled when velocity varies, right? So I'll give you guys a second to write that down here. A particle starts at x equals 0 and moves along the x-axis with a velocity of v of t equaling to t squared for time being equal to or greater than 0. Where is the particle at 3 seconds? That's a mouthful. It's a lot going on in this problem. And we're going to look at it slowly. So let's go ahead, and I'm going to give you a second to write that down, and also a second to copy this graph right here. So I'm going to draw this graph right here. I'm going to make it a pretty big graph. Make that black right there. Okay. And then this right here is going to be a function of time, right? We don't know if it's in meters, seconds, or hours. It just says t is equal to 3 units, let's say. And the height of this problem is going to be velocity as a function of time. Okay. And this velocity as a function of time was actually given to us as t squared. So if you guys are unfamiliar with that, t squared actually looks something like this. That's terrible. Let's do a better job, knock me. No, that's also not good. Hold on a second. I can do this. How's that? Does that look good? Like a nice parabola, right? Because t squared, that's all I'm technically drawing is a parabola right there. Is that okay? Hopefully it's okay. Hopefully you guys can see that all right. So what the rectangular method does, right, is it just basically, remember what we're trying to find is the area to figure out how far this thing has traveled. We need to go all the way out to here. Let's say this right here is t equals to 3, which is the spot right here. Okay, so I'm trying to calculate the total distance this thing's traveled. Yeah, but what I have right now is when t is equal to 3, all I have is that this height right here, this is going to be equal to 9. How do I know that's equal to 9, by the way? Does anyone have any ideas? How do I know that this right here is equal to 9 when t is equal to 3? What's helping me figure that out? It's 3 squared. That's right, Monica. The function of velocity, right, or the height at which I'm at here is all based off of this equation right here. V of t is equal to t squared. So, for example, if I was looking at time equals to, let's see, let's make this even here. Let's make that 2. Oh, that's terrible. Hold up, Knockme. You could do a better job here. 1, 2, 3. So let's see here, like 1, 2, 3. That looks better, right? 1, 2, 3, right? Does that look okay? I think it does. All right, so check this out. So what's this height right here at t equals 2? How tall is this thing? This thing is going to be a height of, you guys see it? 2 squared, or in other words, 4. And this right here at 1, that's going to have a height of, well, 1 squared, which is just 1. Right? So at t equals 1, velocity is going at 1 unit per time squared, right? And then at 2, it's going to go 4 units per time squared, or per time. And then this will be 9 units per time. Now, check this out. If I just draw my rectangle from there, right? If I just draw my rectangle from there, ready for this? I can kind of estimate this area. You ready? If I make my rectangle right here at this dot and I go like so, can you guys see that rectangle? That has a rectangle that has a height of 9, right? It has a height of 9 and has a base of 1. Can you guys see that? And then if I do, so that right there, this gives me this first rectangle that I've drawn right here, right, would give me an area of 9 times 1. Now, of course, this is an overestimate. I have all of this extra area, don't I? But that's all it is. It's just an approximation, right? This is what I'm doing right here. I'm writing out a rectangular approximation. I'm approximating the area underneath here so I can calculate how far this particle moves along the x-axis. Right, so let's go approximation, right? So right here, this is my first approximation. This is my first rectangle that I have. The second approximation I'm going to have is going to be right here at this point right here. Boom. This right here has a height of 4 and a base of 1. See that? Has a height of 4 and a base of 1. All right, are you guys able to see what I'm doing here? I'm making a rectangle based off of these heights. Now, I know that you're like, but knock me, there's a curve here. And again, I'm just approximating, right? So that area right there is 4 times, it's a height of 4 with a base of 1. And then this last one right here, boom, this one right here has a height of 1 with a base of 1. Now, if I add all these together, this will give me an approximation of the area. Now, let me ask you guys in the chat, is this going to be an over approximation or is this going to be an under approximation? What do you guys think? Just by looking at it. Monica's like, over. Clearly, Brian, over. Yeah, it is going to be an over approximation, but it's still an approximation, isn't it? It's still a little bit better, right? Still a little bit better. Now, this is going to equal to, let's see here, 9 times 1 is 9, plus 4 is plus 1. Well, that's going to give me an area of about 14 units. That's how far this particle has traveled, about 14 units. But we know, thanks to everyone noticing right here, that this is a over approximation, and that's okay. It'll happen, but it's still an approximation that's getting made there. Now, here's the thing. How many rectangles did I draw for this problem? Can you guys count it? How many rectangles did I draw? I drew 3 rectangles, didn't I? So here's the thing. if you decrease, that's not the right word. If you increase, wow, that's the complete opposite word of what I'm thinking, Nakmi. If you increase the number of rectangles you have, you will have a better approximation of the area that you're looking at. Right now we have 3 rectangles, right? Because I just went from 1, 2, and 3. Can you guys give me some other equal numbers I can put in between those guys so I can make it so I have 6 rectangles instead of 3? Can you guys help me out? Help me out here. What's something I could do to make this so I have 6 rectangles instead of 3 rectangles? What are some numbers I can add into the x-axis here, where the t is? What are some numbers I can add in there that will make that so I have 6 rectangles? Monica's already going with it. If I add a tick mark, right, I'm going to do this one in red this time. If I add a tick mark at here, which is 0.5, a tick mark at 1.5, and a tick mark at 2.5, I can draw more rectangles. You ready for this? So I'm going to do that right now. I'm going to go ahead and draw a tick mark right here and then go up to here and make a rectangle like this. Now you see that right there, that little rectangle right there, right, is going to help me calculate this area right here. Now, of course, this is still going to be an over approximation, but look, guys, look, it's not as much as the over approximation when I had only 3 rectangles. You see how much blue there I'm leaving out, right? So help me out here. This right here has a base from here to here. What's that base from here to here? What is that base? That's a base of, what do you guys think? What is that a base of? It's a base of 0.5. That's right, guys. That's right. It has a base of 0.5. So I'm doing the same calculation right now. I'm doing the same calculation, but now my base is not 1, but it's instead 0.5, isn't it? Isn't it? Now, what's the height? What's the height? Now, there's a tricky question right there. What is that height at 0.5? Anyone know? What's that height at 0.5? What is it, guys? What is it? 0.25, Brian. 0.25. How'd you get that? Because of t squared. That's right, guys. Use this function here. To get the height of this thing at 0.5, this thing goes up to 0.5 squared. 0.5 squared is that height right there, which happens to be 0.25. 0.25. So that right there, that's the first rectangle that I have there. You see that? Then I go to my next rectangle. I'm going to add that to this as well. My next rectangle is I'm going to go 0.5 over to here. So my next one is going to go to 1. I'm going to calculate that height from here to here. And that's going to be this rectangle right here. See that rectangle? It still has an overestimate, but again, I'm leaving out that extra estimate that I had when I had 3 rectangles. So this one still has a base of 0.5, doesn't it? Because it's going from 0.5 to 1. So that base is still 0.5, right? But the height here is going to be 1 squared. And 1 squared is still, why? It's still just 1, isn't it? So that's this area right here. You see that? That's that area right there. That's essentially what I've just found. I'm going to take that highlight off. All right. I keep going. I keep going. How about from here to here? Why, this right here is going to be 1.5. That's going to give me this new rectangle like so, which again is an overestimate still, but is not as much of an overestimate as when I had 3 rectangles. You see that? So I want to calculate this rectangle now. This rectangle, again, has a base of 0.5, has a base of 0.5, but it has a height of, who wants to tell me what this one? What's this height right here? What would this height be? This one right here. What would that height be? Anyone have any ideas? 2.25. How'd you get that one, Monica? And Brian's got it as well, 2.25. How did you get 2.25? 2.25, that is right. And it's 1.5 squared. How do we know that we're supposed to be squaring this? Because they tell us that's the function at which the velocity is traveling at. So if I know the function of that curve that we're dealing with, we can estimate the height of the velocity at any particular time, right? Just by plugging in the time into that function. And when we do that, we end up with these guys right here. This is a little bit ugly. Let me rewrite that a little bit so it looks a little bit better here. This is 1 times 0.5, and then this is 2.25 times 0.5. Now you notice these three right here, these three little equations here are these three rectangles. 1, 2, 3. That's what we got here. This equation, this right here, and this right here. So far, we've calculated halfway through. Okay, let's keep going. Let's keep going. This right here is the next rectangle I'm going to draw. It's going to go from here to here, like so. And again, it has that overestimation, but it's not as bad as before. So I'm going to calculate this guy right here. That's going to give me the next area, which is going to be 2 squared, which is going to be 4 times the base of 0.5. Okay, times the base of 0.5. And that's this one right here. Keep going. Keep going. Next one up. At 2.5, it's going to give me this rectangle like so. Like so. That's that rectangle right there. And 2.5 squared. Who's got a calculator? Who's got 2.5 squared? What is that? Brian's saying it's 6.25. That has a height of 6.25 right there. All right, I'm going to write that down because I have a little bit of space now. 6.25 is that height times a base of 0.5, right? That's going to give me this area right here. From here to here, that's going to give me this area right here, including that extra, right? So let's go ahead and do that right there. So are you guys starting to see what I'm doing here? I'm using rectangles to approximate the area underneath this curve. Now it's an over approximation, albeit, but it's not too bad, right? It's not too bad. Let's keep going here on this last one right here. This is going to go from here to here, which is another 0.5 distance away. But this time it's going to go up to this height. And this height is what, guys? What is that height for that last rectangle right there? It's going to be at t equals 3. And that's going to give me a height of 9, right? It's going to give me a height of 9. So 9 times 0.5, like so. And that's going to be the last rectangle. So we have here, if you guys can see it, right? We have 6 total rectangles here. The first rectangle, second, third, fourth, fifth, and sixth rectangles. I'm going to take those numbers away though, because it's going to look confusing with those other numbers, but that's the first, second, third, fourth, fifth, and sixth rectangle, right? So if I add all of these together, it's going to give me a better approximation. It's going to give me a better approximation. So I just plug this into my calculator, right? So I'm going to go ahead and do that real quick. So I have here 0.25 times 0.5, right? That's going to be, of course, added with 1 times 0.5, right? Plus 2 point, no, not parentheses, guys. 2.25 times 0.5 times, I'm sorry, plus 4 times 0.5. Of course, you guys, if you already know the halves of these, you don't have to do this whole thing, but I'm just showing all of this work. 6.25 times 0.5, and then, of course, last but not least, plus 9 times 0.5. And we get here, after adding all that up, we get an area of 11.375. And I'm hoping that kind of makes sense. It's pretty close to that 14, isn't it? But what do you notice? It's smaller than that 14, right? And does it make sense why it's smaller? Does it make sense why it's smaller? You're losing out on what? These extra blocks that get cut off. You see it? This technique, this method of rectangular approximation has a name. The name for this technique right here, we call this Rram. Rram. Why do we call this Rram? Well, the Ram part, you can actually get the name from this part right here. This is called the rectangular approximation method. Rectangular approximation method. What do you guys think this R stands for right here? What do you guys think this R stands for right here? And I'll give you a little hint. When you look at this base right here, the height of this base right here comes from this value right here. It comes from that value to get that. Random access memory. That's not it. Look at this base right here. You see this rectangle? The height is on this side of it. Same thing with this base right here. The height is on this side. How do I get this height? The height is based off of this side. This side. What side? That's the right side. Yeah. Great random access. Stop it, David. Stop it. Rram stands for the right rectangular approximation method. All right, so when you look at the right value of that rectangle, you go based off of what that number is on the right, and you calculate the height of that rectangle based off of what the function output value is on that side. That's what the R stands for. So you use Rram to calculate the rectangular approximation using the height of the right side of your rectangle. That of course leads me to the next one, which we call Lram. What do you guys think Lram stands for? Don't overthink it. R over here stands for the right rectangular approximation. L is going to stand for the left rectangular approximation. Left, whatever you said previously. Yes, rectangular approximation. Yes, yes. So if we do Lram, we're looking at the left rectangular approximation. Okay? So let me show you what that looks like. So that means I got to redraw this drawing right here. Can I cheat? Can I just copy and paste this? I mean, I know you guys can't, but can I? Oh God, it's so laggy. Nah, that's not too bad. That's not too bad. Let's start erasing some of these things though. We don't need all this right here because I already have that drawing up there. Oh, I know what I could do. I could just zoom in and erase at a finer level. Oh no. Try that again. Come on, get out of there. It would have been easier if I just redrew this, huh? I think it would have been easier if I just redrew this. But no, Knock Me, you had to be extra. There we go. Right, and let's get the base here. Yeah, I probably should have just redrew it. Oh well. So this right here from 1, 2, and 3. If I instead decided to go with the Lram instead of the Rram, right, I would do the same thing. Let's go with 6 rectangles again, though, because like we said, 6 was a little bit a better estimate. So the values we had here was 0.5, 1, 1.5, 2, and 2.5. Right? Now, if I go with Lram, and David, yes, you are beating me to it. There is one called Mram, and it's exactly what you think. It'd be the middle, but we don't say middle rectangular approximation. We call it the midpoint because we use the middle point. I know, but yeah, let's focus on this one right here. Let's go ahead and look at this Lram right here. So here's the first base right here, right from here to 0.5. But I'm going to look at the left value. And the left value is going to be looking at v of t equaling to t squared. The left value is, of course, 0, isn't it? So what's 0 squared? Why, Knock Me? That's just 0. So this first rectangle is this line right here, which has a height of 0. You see that? So that's going to be 0 times a base of 0.5. And then this right here is the next base from here to here. And again, I'm looking at the left value, which is going to be right here, and gives me that right there. And that's going to give me a height of 0.5 squared, which is 0.25 times 0.5, right? Keep going. From here to here, that's going to be the left side right there. That's going to be this rectangle right here that goes like this, right? Which is going to be 1 times 0.5, right? Keep going. Keep going. This right here has another base that goes on the left side. I'm looking at this height right here. Are you looking at all these rectangles that I'm drawing with my Lram? What do you notice about all these rectangles here? They're all what? Well, that one's poorly drawn. Hold up. This one goes to this height right here, and it goes like that. There we go. These are all smaller than it, right? So the approximation for this one is going to be an under approximation, isn't it? It's going to be an under approximation. But yeah, that's exactly it here. So this is 1.5 squared, which is going to give me a value of, you guys told me 1.5 squared is 2.25, right, times 0.5 right there. This one, the next one right here is going to be at 2, and it's going to go to here, right, for this guy, because it's on the left side. And that's going to be plus 4 times 0.5. And then this one right here is going to be the last one. It's going to go up to, or 2.5 and go over here. And that's going to be 2.5 squared, which is 6.25 times 0.5. So I have here still 1, 2, 3, 4, 5, 6 rectangles still, don't I? I still have 6 rectangles, right? 1, 2, 3, 4, 5, 6 rectangles, right? But it's an under approximation, yes. Now, if you do these calculations and you calculate it out, let me see here. I think I have this number calculated beforehand. This right here, I don't have calculated, actually. I'll leave that up to you guys to calculate it, how much you get out of that and how much more of an under approximation it is. But I'm going to pose this question for you to think about. Do you think Lram is always going to be an under approximation? Do you think Rram is always going to be an over approximation? And I'll leave that for you to ponder and to wonder about. But the last one I wanted to show you is going to be Mram before I let you go today. Right, the last one I want to show you is Mram. I'm just going to redraw this picture because copying, pasting, and erasing it was a little bit too much work. So let's go ahead and redraw this one. All right, from t, this is v of t equal to t squared. Let's go ahead and redraw this one so it looks something like that. All right, I could do better. There we go. So this is going to go from 1, 2, and 3. All right. This one's a little bit different here. Let's do this last example here. We're going to call this one Mram. And again, M stands for not middle. It actually stands for the midpoint. Midpoint. So you ready for this? Here are my 6 rectangles, okay? So just like before, right? It would be at 0.5, 1, 1.5, 2, 2.5, and 3, okay? But here's the thing. My first rectangle, right, should be between 0 and 0.5. To get the height of this rectangle, I need to use the midpoint. So the midpoint that's between 0 and 1.5, who's got that for me? Who can tell me what the midpoint is between 0 and 1.5? 0.25, that's right, 0.25. That's this value right here, and that's going to be this value right here. And that one right there is going to tell me, if I zoom in there, that one right there is going to tell me what the height of this rectangle should be. See that? That right there will tell me that. But to get that height, I would just take 0.25 and square it. Who knows what 0.25 squared is? I'll be honest with you, I don't know what 0.25 squared is. Do you guys know what 0.25 squared is? I'm going to cheat and look at the calculator. 0.25 squared is technically 0.0625. All right, I cheated. I just looked at your guys' answers. That's what that height is. That's what that height is, right? So that's the idea behind the midpoint. You got to calculate how many rectangles do they want us to make, first of all. And they want us to make 6. Well, I'm just making up 6 in this case. And the way they denote this, by the way, is they're always going to have like a little number. So for Mram, if I want it with 6, they put a little 6 behind it. These other ones up here, this is technically Lram with a little 6 because they wanted 6 rectangles. So I'm going to go in here and I'm going to draw 6 rectangles. But before I draw the height of the rectangles, I just draw the bases of my rectangles first, right? So there's 1, right? There's another one. That's 2. That's 3. That's 4. That's 5. And that right there is 6. You see that? But to get my heights, I don't use the left value or the right value of these things. Or in this case, the left value or the right value. I don't use those guys. I use the middle point between those values. And Monica was kind enough to give me the one that's between 0 and 0.5, which was 0.25. Who's kind enough to give me the next one between 0.5 and 1? What's the next value between 0.5 and 1? 0.75. That's going to be right here, right? 0.75 is right there. 0.75 is between 0.5 and 1. So let me ask this next question then. What's the height of this next rectangle? What's the height of this next rectangle? Well, it's 0.75. You probably thought it. It's 0.75 squared. And again, I don't know what 0.75 squared is, so I'm going to cheat and plug it into this calculator over here. Oh, or Monica. I'll plug it into this Monica over here. Monica says it's 0.5625. All right, that's what that one is. I'm just keep going here. This next one right here would be 1.25. This one right here is going to be 1.75. This one right here is going to be 2.25. And this midpoint right here is going to be 2.75. And to get these values right here, I hope you guys can see this. When you do the middle rectangular approximation, I hope you guys can see it. It gives you a little bit of an overestimation and a little bit of an underestimation each time. You see that right here? When I go to the middle right here, it goes a little bit over and it goes a little bit under. Over here, it's a little bit over and a little bit under. And this last one right here, we go a little bit over and a little bit under. Mram is probably one of the better ones out of the three that we have right here between Rram and Lram. But yeah, to get these out here, I'm just going to cheat a little bit. I have these numbers calculated already here. So this is going to be 1.25 squared, which is going to be 1.5625. 5625. This one right here is going to be 1.75 squared, which comes out to be 3.06252. 6252. 2.25 squared comes out to be 5.0625. There's probably more after that. And then 2.75 comes out to 7.5625. 7.5625. So what's better, LRAM, RRAM, or MRAM? And that's not a valid question, by the way. They're all just approximations, okay? One will overestimate, one will underestimate, and MRAM kind of is in between. Sometimes it's overestimated, sometimes it's underestimating. It all depends at how much the curve is affecting. How much of a curve do you have? How much of a concave up or how much of a concave down you have, okay? By the way, if you were to calculate this, approximately comes out to about 8.9375. If you just want those values there. So that's the idea here. We still haven't really gotten into the calculus part of this here. We've just broken down a shortcut for us to be able to calculate area for these curves, right? A method that will help us calculate that, right? And this method is to draw rectangles, and the more rectangles we have, the better approximation, right? The more rectangles we have, the better approximation. Because when we started off, right, we started off with RRAM. We started off with RRAM up here, right? But with that RRAM, it was RRAM with 3 rectangles, right? And that gave us the 14, right? But then when we went with RRAM with 6 rectangles, that gave us 11.375, right? And then when we did LRAM, we got this guy right here, which I did not calculate. And then we got MRAM. And MRAM gives us a pretty close approximation of 8, right? How far did that particle travel? It traveled about 8 units, 8.9 units. David, SRAM, short rectangular approximation method. Not necessarily short. Short talks about the height, and the height is going to be set to whatever the function is, but you're getting the right idea. Instead of short, you're thinking something else. The more rectangles you have, the narrower the base, right? The narrower the base. And if you can picture it, when these bases get more and more narrow, there'll be less and less over/under approximations, which will make it a lot more accurate when you do these approximations. All right, guys, I think that's going to be it for today. The homework that I'm going to assign for you guys tonight is going to be asking you to look at some functions and calculating Lram, Rram, and Mram, right? Isn't that just fun to say? Lram, Rram, and Mram. Let me show you right here real quick. So let me do that right here. Your homework is going to be right here in 5.1. Let me do that right now before I forget. It says that it's due next week, but you know the deal with me. Just do it whenever you can. Don't let the homework stack up and pile up in this class, right? I will accept them late, but please make sure you don't wait until the end. You're going to end up hating yourself for it. So let me go ahead and put this link right here so I don't forget. 5.1, estimating sums homework. There you go. And save. All right. And I'm going to wrap it up there. We're going to continue with this whole idea behind Lram, Rram, and Mram. But I'm going to leave you with this question right here, right? Is Rram always going to be an over approximation? And if so, can you prove that to me? And if not, can you find out when is it not going to be an over approximation? And with that being said, once you find that out, what can you say about Lram then? Is Lram always going to be an under approximation? And if so, can you prove it? And if not, can you show me an example when it's not going to be an under approximation? All right, so think of an example when that's the case. But yeah, we're going to wrap it up there. I'm ending a little bit early, but that's going to be it for me today. Hopefully this wasn't too bad of an idea, but can you guys picture the calculus that's going to go into this yet? The more rectangles you have, the better your approximation. What would make this a calculus problem then? Anyways, I'm going to leave it at that. I'm going to leave it there, and we'll continue on Thursday. All right. Have a good rest of your day, guys. You got the homework that you can work on today, and that's it. I'm going to end it a little bit early. I'll see you guys on Thursday. Have a good rest of your day. I'll see you guys later. If you have any questions, I'll be in my office hours today. I will have office hours today from 1 to 2. Yeah, I'll be there. So let me know. Please stop by. If you haven't taken the test last week on Thursday, let me know when is good for you. And other than that, have a good rest of your day. Oh, if you didn't do the quiz, stop by as well yesterday, or the quiz from yesterday. All right, anyways, see you guys. So long. Farewell. Bye-bye.